Jai Hind everyone. This is Dr. Naresh Kumar from Akgec Engineering College, Ghaziabad. Welcome to the class of Communication Engineering under Unit 1. In this lecture, basically we will cover the topic Introduction to Communication System and Amplitude Modulation. Basically in this lecture, we will study what do you mean by the communication engineering, what are the various blocks required to make a communication system, and what is modulation, what is the need of modulation, and what is amplitude modulation and various relations for the case of amplitude modulation. We will also study the concept of modulation index here. So first of all, in this lecture, what is communication engineering? Basically, I am saying you are listening, that is also communication. But this is not communication engineering. Basically, communication engineering is the process of conveying information from one place to another place, and most importantly, we have to use via electrical or electronic means. That means we will say the message is being conveyed from one place to another place, and we have to use some kind of components, device, equipments or processes in between the source and destination. That we can say that we have to use some kind of transmitter, some kind of receiver and some kind of channel or media for carrying the information from receiver, from transmitter to receiver side or from source to destination. So, normal conversation is not communication engineering. Communication engineering involves use of transmitter, receiver and some kind of channel or media. The channel may be, for example, can be wireless, for example, the free space. The channel can be a wired media or guided media, for example, optical fiber cable, coaxial cable, twisted copper wire. And transmitter and receiver can also be there, for example, RF transmitter and receiver. For example, optical transmitter and optical receiver. So, communication system model. So, basically as we have studied, if we implement the definition of the communication engineering with the help of this block diagram, that is the communication system block diagram. So, as discussed, in the case of communication engineering, the information is conveyed from source to destination, and for that we have to use some kind of transmitter, some kind of channel or media and some kind of receiver. So, on the transmitter side, let us say we have the input message. This input message can be converted into the desirable form, one form to another form with the help of some kind of input transducer. We know that the transducer converts the input message into the electrical signal. So, one form of energy is converted into another form with the help of this transducer. For example, we can use microphone as the input transducer in the case of sound. That is, for converting sound into the electrical form, we will use the input transducer. For example, that can be the microphone or mic. After that, we will use the transmitter. In the transmitter, we will basically use the most important process known as the modulation. That is, in the transmitter section, we will use the message signal and a carrier signal. After that, the modulation process will be used and the modulated signal will be transmitted from the transmitter into the channel or media so that it can be easily transmitted through the channel. As we know that this channel can be wired or guided, or maybe wireless channel. As we have discussed, for example, the wired channel can be, for example, coaxial cable, optical fiber cable, copper wire twisted pair, or in the case of wireless, it may be the free space. Now, the noise and distortion gets added up with the transmitted message signal in the channel. On the receiver side, the received signal is received by the receiver from the channel, and in the receiver, basically all the processes occur which are reverse in nature of that happen in the transmitter side. For example, in the transmitter side we have used the process modulation. So here we will use the demodulation. Okay, and as we know that here we have added some kind of distortion and noise, etc. So these needs to be removed from the from the signal in the receiver. So for that purpose, additionally we can use here, as to remove the noise we can use the filter, and to remove the distortion we can use the equalizer, and if the magnitude of the received signal is not very high, so in that case we can also use some kind of amplifier in the receiver side. That's why the structure of receiver is more complex as compared to the transmitter side, because we need these additional blocks for getting the desired message signal as it was available on the transmitter side. And finally, we will use the output transducer as we have used on the input side. For example, on the input side we have used mic for converting the sound into the electrical form. So again, if we have to convert back electrical signal into the sound, so we have to use some kind of loudspeaker. So loudspeaker can be used as a output transducer. Okay, and finally the information reaches to the destination site. Now next is most important process, modulation. As we have discussed in the previous slide in the communication block diagram, on the transmitter side the most important process is modulation. Basically, in the communication system we use a message signal which is generally a low frequency signal. Then we use a high frequency carrier signal which is generally a high frequency. In the next slide we will study what is the need of modulation, why the modulation is required. So basically in the modulation process we change or vary the characteristics of this carrier signal according to the instantaneous value of this low frequency message signal. That is, in the communication system we don't transmit the message signal directly as it is. In fact, it is transmitted with the help of a high frequency carrier signal, where the characteristics of this message signal are superimposed over the carrier signal. Or by definition we can say that the modulation is the process is by varying the characteristics of the carrier signal according to the instantaneous value of message signal. So the characteristics of carrier signal that can be varied. For example, we can vary the amplitude of carrier signal, we can vary the frequency of the carrier signal, we can vary the phase of the carrier signal. So these are the characteristics of carrier signal which are modified or varied according to the instantaneous value of message signal. So this process is known as the modulation, or we can say that in the modulation process basically we superimpose the information onto a carrier signal. Okay. So next is examples of modulation. Here we have shown two examples. One, this is the amplitude modulation, this is the frequency modulation. As we have studied in the definition, in the AM, amplitude of the carrier signal is varied according to message signal. So here we can say that the amplitude is high, amplitude is low, again amplitude is high. So amplitude is changing. In this case, the amplitude is constant. In the case of frequency modulation, the amplitude of the carrier remains constant, whereas the frequency of the carrier signal is varied. So we can say that here we have the low frequency, here we have the high frequency component. So the frequency of the carrier signal is varied according to message signal. So these are the AM, amplitude modulation, and FM, that is frequency modulation, are the two examples of modulation process. Now the question arises, what is the need of modulation? Why don't we transmit the message signal directly without the help of the carrier signal? And another question arises, why we use a high frequency carrier signal along with the message signal? So the answer for that is, what is the need of modulation, or why modulation, or we can say that why the frequency of the carrier signal is high. So the main reasons are, first important reason is to ensure the practicality of the antenna, or we can say that to reduce the antenna height, size or dimensions. Basically we know that the size or dimensions of the antenna are given in terms of lambda. For example, lambda by 4 quarter dipole antenna, half dipole antenna is lambda by 2. So antenna size is given by this lambda by 4 or lambda by 2, and we know that f equal to c lambda, that is lambda equal to c by lambda equal to, so f equal to c lambda, and so we have f equal to, so we can say that this lambda equal to c by f. So there is inverse relationship of this frequency with the wavelength. So whenever the frequency is high, this lambda will be low, and whenever this lambda will be low, then the antenna dimension will also be less. So we can say that this, whenever the frequency of the signal is high, the lambda will be low, and if lambda is low, the dimensions of the antenna will also be low. And if dimension of antenna is low, that is less material is required, it will occupy less space and it will cost less. So to get these advantages, we ensure the signal frequency should always be high. That's why, because the message signal has a low frequency, so that's why we use a carrier frequency of high in value as compared to the message signal for carrying the information signal using the modulation process. Then another advantage is it avoids intermixing of signals. That is, for example, generally the audio signals lie in the same range. If we directly transmit those two signals, they will intermix with each other. To avoid this intermixing, we use modulation process and we transmit these using different carrier frequencies FC1 and FC2. So if we use different carrier frequency for the two signals, then there will be no intermixing of signals. Another advantage is frequency multiplexing, or simultaneously transmission of multiple signals over the single channel or using the single antenna, that is to achieving the narrow banding. So to achieve this frequency multiplexing or narrow banding, we use the modulation process or carrier frequency high. Another is for achieving the long distance communication. We know that the power of the signal is directly proportional to its frequency. So more is the frequency of the signal, more is the power, and it will cover a longer distance. If we transmit the message signal directly, then the frequency is low, so it will not cover the long distance. So in applications where the long distance communication is required, modulation is a must. Another advantage of using the modulation or high frequency carrier is to improve the quality of reception by reducing the effect of noise. We know that if we use high frequency carrier, then the power of the signal is more, and if power of the useful signal is more, it will be very less affected by the noise. So the effect of noise gets greatly reduced in when we use the modulation process. So because of these advantages, there is need of modulation, or we do not directly transmit the message signal over the channel without using the carrier. And more importantly, we have to use the carrier with a high frequency. So next is amplitude modulation. As discussed, we have to vary the characteristics of the carrier signal according to message signal. So in the amplitude modulation, we vary the amplitude of the carrier signal, according to instantaneous value of the message, signal. So we will vary the carrier amplitude according to message, that is amplitude modulation. Or we can say that it is double sideband modulation or double sideband with full carrier. Basically, when we see the equation of the amplitude modulation, we will see that the output equation has a carrier and two sidebands having the same information. That's why this AM is also known as the double sideband with full carrier. This is the example. In the previous slide, we have seen the message signal. This is the high frequency carrier signal. This is the amplitude modulated AM wave. We can see that this is the carrier, though the carrier amplitude is changing according to message signal. Okay, so the amplitude is continuously changing as the change in the message signal. So when the message signal, this was our message signal. So whenever the amplitude is increasing, so here we have the carrier amplitude increasing, then we have decreasing, then we have the decreasing. These are shown in a single diagram. This is the message signal. This is the high frequency carrier signal. This is the AM wave, amplitude modulated wave, where the amplitude of this carrier signal is varied according to this message signal. So we can see the derivation for the AM. First of all, we have message signal mt equal to Vm cos of omega mt. Then we have a carrier signal Ct, Vc cos of omega Ct. Then by definition, we have amplitude modulated signal where we have the amplitude of the carrier signal is varied according to the message signal. So basically this is the carrier signal and its magnitude Vc is varied according to the message signal. So putting this in the equation, so we have Vc and putting the value of mt here from this equation, we have Vm cos of omega mt and putting this value, and after solving this we get Vc cos of omega Ct into 1 plus Vm Vc cos of omega mt, where this relation Vm by Vc is most important, and this is known as the modulation index. Modulation index. Basically, we are changing the characteristics of carrier according to message. So here we are changing the amplitude of the carrier according to message. So this gives as a measure of change in the amplitude of the carrier signal according to message signal. That is how much modulation that we have performed, that extent is measured or given by the modulation index. Basically this can be a value or this may be given in terms of percentage. This modulation index for the case of AM, for example, can be less than 1, equal to 1, or maybe greater than 1. These two are the case of linear modulation, where this is called under modulation, this is called as 100% modulation, and this is called as over modulation. So solving this equation, putting this value Vm by Vc as modulation index. So expanding the equation, we get this one using the cos equation. Then finally we have the AM equation as this equation. From this we can see that this first component is Vc cos of omega Ct, that is carrier. Another component is Ma Vc by 2, that is with frequency omega C plus omega m, carrier plus sum. And then we have Ma Vc by 2 cos omega C minus omega m. So plus omega C plus omega m, omega C minus omega m. So basically we are getting two sidebands here. This omega C plus omega m factor is, here we have upper sideband and this as the lower sideband. Basically if we implement this equation in the frequency domain, we get the spectrum of AM signal like this. We have Fc at the center, then we have Fc plus Fm as the upper sideband. Here we have the carrier and then we have the lower sideband. This is Fc minus Fm. This is the carrier. Okay. So the magnitude of this carrier will be Vc, and from this equation the magnitude of sidebands will be Ma Vc by 2. So both the sidebands will have magnitude as Ma Vc by 2. So this magnitude is also Ma Vc by 2. So this is the frequency domain representation of amplitude modulation or the frequency spectrum of AM wave, where we have the carrier at the center and the two sidebands, lower sideband and upper sideband, and both of these sidebands having the same information. This is the, as discussed in the previous slide, this is the frequency domain representation, or we can say the spectrum of AM wave. Okay. Then the bandwidth of the system is, this is the range of frequency, that is the bandwidth of the system. So bandwidth of the system will be given as Fc plus Fm minus Fc plus Fm. So it is 2 Fm. So the bandwidth of the AM system is given as twice of Fm. Fm is the maximum frequency component or frequency component in the message signal. Again, this is the frequency spectrum of AM wave, where we have the carrier at the center, then we have upper sideband and lower sideband with bandwidth 2 Fm. Modulation index, as discussed, this gives us the extent up to which the modulation has been performed. So this ratio Vm by Vc is known as the modulation index, and in percentage modulation it is given as Vm by Vc into 100. As discussed, there can be three cases for modulation index. It can be greater than 1, modulation index can be greater or equal to 1, or modulation index can be less than 1. So out of these three cases, these three are shown here. This is the case of AM with modulation index less than 1. This is case where we have modulation index equal to 1, and this is the case where we have modulation index greater than 1 or greater than 100%. So this third case, modulation index greater than 100%, is known as the case of over modulation. And we can see that the case of over modulation should be avoided, because this can result into distortion at this point. And if we have distortion in the AM wave, then when we demodulate the modulated signal to get the original message signal, it will be very difficult to obtain the original message signal shape. Or we can say that over modulation should be avoided to reduce the distortion effect in the case of AM. So this is the AM wave as discussed. So in this AM wave, we can calculate the values of various factors, like this is up to this point we have the VC carrier frequency, up to this point we have the modulating message signal VM, again this is also VM, this is the maximum point, so this is Vmax, okay, and this is the minimum point, so we can calculate here is as Vmin, okay. So basically in this equation we can calculate from this diagram, we can calculate the value of Vm and Vc, so that we can have the modulation index equal to Vm by Vc. So we will compute the value of this Vm and Vc from this graph or diagram in terms of Vmax and in terms of Vmin, so that we can calculate the modulation index in terms of Vmax and V minimum. So performing these calculations, we can have this modulation index equal to Vm by Vc. So from that figure, previous figure, we have Vm plus Vm equal to Vmax minus V minimum, that is Vm equal to Vmax minus V minimum by 2. So in this case, then we will calculate Vc. Vc is given by Vmax minus Vm. So Vm value can be putted from here, and solving we can get the modulation index in terms of Vmax and V minimum. That is, in the AM wave, if we know the maximum value and the minimum value for the amplitude, we can calculate the modulation index for the case of AM. These are the power relations in the case of AM. So basically, total power in the AM will be given by power of carrier plus power of lower sideband and upper sideband, and carrier power is given by Vc square by 2R, and by calculating we can calculate the power corresponding to upper and lower sideband as this one, and total power can be calculated as this one, and then total power will be given as transmitted power or total power PT equal to Pc into 1 plus Ma square by 2. So this is the relation between the modulation index, carrier power and the total or transmitted power in the case of AM. These are the various relations. In conclusion, we can say that if we put the value of M equal to 1 in previous relation, we can see that the total transmitted power will be 1.5 times of the carrier power. Then we can also calculate the transmission efficiency, that is power corresponding to sidebands divided by the total power is known as the transmission efficiency. So the transmission efficiency is given by this one, that is transmission efficiency will be M square divided by 2 plus M square. And if you put M equal to 1, that is modulation index equal to 1 or 100% modulation, we can have this as 1 by 3. Okay, so we can see that the transmission efficiency is 1 by 3 only, or 2 by 3rd power is contained in the carrier, whereas only the 1/3 power is contained in the sidebands. So hence resulting into the less power efficient. So in the AM we can see that the AM is not bandwidth efficient because it is using 2 sidebands. It is also not power efficient because most of the power is contained in the carrier. That's why we use the single sideband modulation, and we also suppress the carrier. So that's all for this lecture. Thank you everyone. Jai Hind.